This project utilizes fundamentals of the Reynolds transport theorem, specifically with conservation of angular momentum in mind. For the project, we decided to relive one of the problems we solved in angular momentum unit and created a rotating sprinkler device. This rotating sprinkler head features dual adjustable outlets to demonstrate behavior that can be used in many more complex applications. So we started off with designing the sprinkler from scratch using some CAD software. After printing it out in a few pieces, we assembled it and tested it out. Now that we have the sprinkler, we can look at some of the math behind this phenomena and carry out a small experiment. First, we can define some basis vectors and physical variables relevant to the system. Then we can jump into the math by starting with this momentum expression. We can use approximations of steady state and no external torque and define the relative velocity, velocity control volume, and rest frame velocity. Cross product in the previous yields a z component only since the sprinkler head can rotate about only one axis. Looking back at our equation, we can see that due to geometry of the dotted vectors, we can bring out all terms of the integral, multiply this by 2 since there are two outlets. Omega is then a function of the angle alpha. So omega is proportional to the cosine of alpha, which then should hold both theory and in trial. The left equation is not that accurate experimentally, though, due to leakage and frictional forces. Regardless, we have upper and lower bounds at 0 and 90 degrees. This gives us the following relations. From this, we carry out an experiment. Experimentally, we'll use two intermediate angles of 22.5 and 45 degrees, so we confirm what theory is telling us. For the experiment, I used some water hose water as a fluid and a foam stand with some tape and tubing attached to the sprinkler. To record the angular velocity experimentally, I designed a simple grid and used the video timing information to capture how many rotations were present in a 2-second interval. To see how the speeds vary visually, we can play the recordings of the rotation for each angle simultaneously. Do you notice how they're out of phase? Allow me to play it again, but at a slower speed. The angular speeds for each outlet angle were clocked in using the special grid that I mentioned earlier, and the results were as follows. As you can see, these results lined up with what theory predicted. The experiment was a success. Before we move on to some other applications of angular momentum, we can better graphically visualize their velocities. I have converted them to radians per second and plotted them in a time series.
There are many other applications that rely on the conservation of angular momentum. Take spacecraft or satellites in orbit. Ideally, their movement can be predicted by the Keplerian orbit model, in which angular momentum is conserved at each position in an elliptical pattern. Other engineers have also put the principle to good use, like an inventor Michael Carew's angular momentum engine. His design can produce anywhere from a few to 1 million pounds of linear momentum that is generated by using a planetary gearbox's angular momentum. Our sprinkler model demonstrates this fundamental element of fluid mechanics that affects various different fields of engineering. If you can understand this principle by observing our model rotate, the door is open for endless capabilities of what you can do in the future with your new fluid mechanics knowledge. Thank you.